Hey everyone, and welcome to this explainer. Today, we're taking what looks like a totally standard, maybe even slightly intimidating grade 12 physics exam, and we're going to flip it on its head. We're revealing it to be something much more profound. It's literally a manual for how the universe operates. And honestly, once you view reality through this lens, you simply can't unsee it. So let's dive right in. Okay, to kick things off, let's ask a few fundamental questions about everyday phenomena that seem, well, completely unrelated. Why do astronauts appear to just float weightlessly in space? How on earth can a colossal heavy steel ship sail gracefully across the ocean without sinking like a stone? And why does sweating on a sweltering hot day actually cool you down? Well, it turns out the secret to all these mysteries lies hidden right in the curriculum of a standard physics exam. It's essentially a decoder ring for reality. We're going to use it today to see exactly how these invisible physical laws dictate absolutely everything around us. Here is our syllabus for today. We've got 4 distinct chapters. First, the pull of gravity. Then, mastering fluid mechanics. After that, the rules of heat, and we'll wrap it all up with engines and thermodynamic cycles. All right, let's start with chapter 1 and the foundational mechanics of the universe, the pull of gravity. So, getting back to our astronaut question, there's actually a huge misconception out there. Astronauts aren't actually in zero gravity at all. No way! They are simply in a state of continuous, endless freefall around the Earth. They're falling, sure, but because of their incredible forward horizontal speed, the Earth literally curves away beneath them at the exact same rate they're dropping. It's wild to think about. To really understand how that gravitational pull works, we have to look at this number. This staggeringly tiny number, 6.67 times 10 to the negative 11th power, is the gravitational constant, or g. It represents a universal, unbreakable rule dictating that absolutely everything with mass exerts a pull on absolutely everything else. Yes, that literally means you are gravitationally attracting your coffee mug right now, just, not quite enough to actually move it. Picture this in practice. If you have a 10-kilogram mass and a 20-kilogram mass sitting just a few feet apart on the floor, they actually exert a precise, calculable pull on each other. Now, at that scale, it's an incredibly tiny force. But scale those masses up to planetary sizes, suddenly it becomes the architect of the cosmos. It's exactly why the moon, despite being way smaller than the sun, bullies Earth's oceans into massive tides, simply because it's so much closer to us. Okay, moving from the cosmic dance of gravity, let's bring things back down to Earth for Chapter 2, Mastering Fluid Mechanics. There are 3 core invisible rules dictating how liquids and gases behave. First, Archimedes tells us that a massive steel ship floats because it displaces a volume of water equal to its own weight. Then we have Pascal's principle, which governs how pressure works in confined fluids. And finally, Bernoulli, who links a fluid's velocity directly to its pressure. Now, what's truly fascinating here is how human engineering takes these rules and manipulates them. Take a hydraulic system, for example. Pascal's principle states that any pressure you apply to a confined fluid is transmitted equally in every single direction throughout that fluid. And here is the sheer magic behind that system. If you apply a small amount of force, let's say 100 newtons, to a tiny input piston, the fluid transmits that exact pressure everywhere. But if you connect it to an output piston that happens to be 10 times larger, well, that output force suddenly becomes 1,000 newtons. We're essentially tricking physics into multiplying our strength, letting us lift massive, incredibly heavy weights with just a fraction of the effort. It's a real game changer. Right, from manipulating the flow and pressure of liquids, let's transition into the realm of internal energy with our third section, the rules of heat. To really master thermodynamics, you have to wrap your head around the idea that heat is basically just the physical movement or jittering of molecules. And that brings us to absolute zero, the profound theoretical temperature where all of that molecular motion completely 100% stops. You've drained the system of all kinetic energy, hitting the universe's ultimate deep freeze. That's actually why the Kelvin scale is the go-to in scientific calculations. It starts right at absolute zero, which completely sidesteps those tricky negative numbers. When we're measuring this energy, we track it through different specific states. For instance, an isobaric process happens under constant pressure. Imagine a gas expanding but not pushing any harder against its container. On the flip side, an isochoric process happens at a constant volume, kind of like heating up a sealed, unbreakable metal box. Now, you might be wondering, why does tracking these specific energy states actually matter in everyday life? Well, consider this. A burn from steam at 100 degrees Celsius is significantly more damaging than a burn from boiling water at that exact same temperature. Why? Because the steam is carrying a bunch of hidden energy called latent heat. When that steam hits your skin and condenses back into a liquid, it releases all of that extra intense heat in one massive go. Adding heat to a system also causes what's known as thermal volume expansion. Basically, as a liquid heats up, its molecules gain kinetic energy and start fiercely spreading out, elbowing each other for room. This expands the fluid's volume without changing its mass at all, which is exactly what physically forces the liquid to rise up inside a narrow thermometer tube. It's a perfect example of microscopic kinetic energy causing a totally visible physical change. And that brings us to our final chapter, Section 4, Engines and Thermodynamic Cycles. A genuinely brilliant example of applied physics is the internal combustion engine, and specifically, the diesel engine. Unlike your standard gasoline car engine, diesel engines don't even use spark plugs. Instead, they compress air so intensely, we're talking incredibly high compression ratios, that the internal temperature of the gas naturally skyrockets right past the auto ignition point of the fuel. Boom. Pure thermodynamics at work, no sparks required. The mechanics of this form a perfect thermodynamic loop, known as the diesel cycle. Instead of just getting bogged down in the textbook terms here, try to think of it as the engine's heartbeat. It fiercely compresses the air, adds heat at a constant pressure, lets that explosive energy expand to do the actual heavy lifting, the mechanical work, and finally rejects the leftover waste heat so it can start the whole shebang all over again. And because this operates as a closed loop, the engine takes in heat, uses a chunk of it to turn your wheels, and then just spits out the rest. Because the entire system perfectly resets back to its exact initial state after every single revolution, the net change in internal energy for a complete cycle is always exactly zero. But hey, you don't always need heavy, complex machinery to harness these laws. Really simple, ancient devices, like the Zier pot, use the exact same physics as your sweat. It cools its contents purely via the latent heat of evaporation. It essentially gives you a highly effective refrigerator that requires absolutely zero electricity. Over time, however, there is a pretty stark reminder built into the second law of thermodynamics, and that is entropy. Entropy measures the molecular disorder or randomness in a system. And the harsh truth is, over time, every engine, every chemical reaction, and yes, every melting ice cream cone proves that systems inevitably lose energy to friction and waste heat. It's a completely irreversible process. So, knowing that nothing lasts forever and that irreversible processes basically rule our reality, it leaves us with one final essential question to ponder as we wrap up this explainer. If the universe is constantly, inevitably moving toward molecular disorder and randomness, what are you going to build with your available energy today? Thank you so much for exploring the mechanics of reality with me. Keep asking those big questions, and I'll catch you in the next explainer.